Hi everyone, my topic today is distributed mission and charging scheduling for UAV swarms to maximize service coverage. My name is Min-Chun Cho from National Yang-Ming Chiao-Tung University in Taiwan. Here is my outline. I will go from the introduction to the conclusion. First is introduction. In recent years, UAVs have been widely adopted as flying base stations to offer sensing or communication services over a large area. Compared to traditional solutions, UAVs have advantages such as convenient and low-cost deployment. Also, UAVs can be manipulated remotely or automatically without a person on board. However, UAVs are restricted by limited energy capacity. So, usually there are two solutions in terms of battery. First is energy-aware design, second is rechargeable UAVs. In this work, we will focus on rechargeable UAVs. Suppose we have a target service area. In this work, we aim to deploy a fixed number of rechargeable UAVs at space station to offer services to them. However, it concerns us that the full service coverage may be unachievable because the number of UAVs is fixed. In addition, an UAV cannot provide any service coverage once its battery is dead. Thus, how to maximize the accumulated service coverage before all UAV run out their batteries is the heart of our work. Indeed, in our work, the problem is extended by assuming that each sub-area might demand different number of UAVs, and neighboring UAVs may have overlapping coverage in the same sub-area. So in the following, we will work on this new problem. To start with, we talk about the system model. First of all, the whole process is split into T-time slots with the same length. Also, the target area is divided into several independent sub-areas. Some sub-areas have one charging station while some don't. And in the charging station, there are charging slots. So, for example, the rightmost charging station has 3 charging slots. Therefore, in the time slot, UAVs might be serving some sub-areas. Charging, resting, or flying. Most importantly, in any time slot, whichever action an UAV takes, there is a way to calculate the amount of the action's corresponding gain and cost. Maximizing the sum of all UAV's gain and cost over the whole process is exactly what we want in this work. Now we are ready to formally define our problem. As mentioned earlier, our goal is to achieve the most service coverage in the course of deploying rechargeable UAVs. But the problem actually comes along with 8 constraints. First, in the time slot, any UAV could be in only one sub-area. Second, the amount of UAVs which charge in sub-area A must not go over SA, which in other words, no vacancy once sub-area A's charging station is full. Third, an UAV cannot serve if its battery comes flat. Fourth, UAV can move from one sub-area to another only when it has enough power, in case it dies halfway. Fifth, every UAV can serve, charge, fly, or rest. Sixth, an UAV cannot rest in a sub-area which lacks a charging station. Seventh, an UAV cannot charge in a sub-area which lacks a charging station. The last one, in the time slot, each UAV's maximum traveling distance is limited. All the constraints and the corresponding objective function can be found in the paper. In fact, it is hard to straight solve the objective function with so many constraints. Fortunately, our proposed mechanisms allows everyone to view the problem from a different perspective. So let's proceed with the proposed mechanism. problem is first formulated into a non-corroborative game like this. In this game, gamma, there are three basic elements. The first one is the player set, which is all UAVs. The second one is every UAV strategy set. And the last one is every UAV's utility function regarding to other UAV strategies in time slot J. To explain clearly, a total of 4 cases will be brought up. The first case specifies that if an UAV intends to fly from K to A and rest there, we first make sure if it has enough power to fly to A. If not, a huge penalty is given. If yes, the flying cost. Also, a resting profit is offered. Note that in our design, an UAV would prefer charging over resting unless the charging station is full, so the resting profit is usually less than the charging gain. And an extra profit to encourage UAVI to charge. The point is, we certainly don't want any UAV to serve at the risk of low power. Hence, the lower the power is, the more UAVI gains from this term. Notice that red number specifies a cost and the green one is a gain. Similar to case 1, case 2, 3, and 4 also have their own ways to calculate the cost and gain. In the second case, UAVI wants to fly from K to A and alternatively charge there. The same if UAVI's residual power doesn't allow UAVI to fly to A, a penalty is given. Otherwise, the flying cost. And don't forget about the extra profit which encourages UAVI to charge. Furthermore, UAVI gets the charging gain from A. Yet, when UAVI is fully charged but insists on charging, a huge penalty is given. So this is in fact a term to prevent the fully charged UAV from occupying the charging slot. It gives us a picture of how the utility is calculated in case 2. Now we move on to case 3. In case 3, UAVI would like to fly from K to A and serve A. Things are slightly different here. We must ensure that it has enough power to fly to A and serve A. Afterwards, still has enough power to fly to the nearest charging station to charge. Let's say if unlike the figure, subarea A doesn't have a charging station, so UAVI will have to fly to another subarea to charge. This is why we need the last check, and then the flying cost. Most importantly, the serving gain UAVI gets from A. Then we're done with the utility in case 3. Now we come to the last case. As addressed previously, an UAV charging and serving at the same time violates our constraints, so nothing but a huge penalty is given under the circumstances. To sum up, the 4 cases altogether makes the final utility function of every UAV. In general, we would have to find out if there is a Nash equilibrium in gamma, where no one will change their strategy. But as a substitute, we equated gamma to an exact potential gain, where at least one Nash equilibrium exists. Roughly speaking, the idea is as follows. First, the game gamma is divided into 3 subgames, which focus on the serving game, the charging game, and the utility function which solely relies on the battery. Then there are proved to be 2 congestion games and a self-motivative game, respectively, which are all classes of exact potential game. With those 3 subgames combined, gamma is said to be an exact potential game, which implies that gamma has at least one Nash equilibrium. If you're interested in the details, the relative proof can be found in the paper. Now, to the best of our knowledge, there is at least one Nash equilibrium in gamma. We get to move on to the proposed approach. In order that the game converges to a Nash equilibrium, UAVs must act sequentially. So first of all, each UAV has its own countdown. Second of all, an up-to-date local copy of other UAV strategies. And third of all, an indicator which indicates if any other UAV has changed its strategy. To simply put, in each time slot, the UAV whose countdown ends first is selected. Meantime, other UAVs are disqualified at once and they must reset their countdowns. In response to the current state, the selected UAV will broadcast its best response strategy to other UAVs. But before broadcasting, it takes a look at DI first. If DI is true, then we've reached the stable state, which is a Nash equilibrium. If DI is false, then some UAVs has changed and broadcasted its strategy. So, UAVI calculates and broadcasts its best response strategy to other UAVs and set DI to be true. You may check out the complete algorithm in our paper. All in all, except for the broadcast strategies, all the operations are done locally, namely, it is a distributed approach. In the following, we will refer to the simulation results. Here, we change the number of charging slots and see how the coverage ratio responds. Be aware that there are two settings regarding our algorithm, 1 and 2. The difference is that the serving game in 1 is less than the serving game in 2. So the simple idea is that the UAVs in setting 2 prefer serving, while in setting 1 they prefer charging. Just bear this in mind as we move on. Speaking of the situation of few charging slots, UAVs in setting 2 tend to serve until their batteries are almost flat. Chances are that the charging slots are all occupied and some UAVs have to wait. Meanwhile, they have no choice but to rest because their batteries are not enough. Consequently, the coverage ratio is bad in setting 2. Yet, in setting 1, even though the charging station is full, an UAV may still have power to serve because it simply prefers to charge even when it loses just a bit of the power. As a result, the coverage ratio with fewer charging slots in setting 1 is better. On the other hand, when it comes to ample charging slots, UAVs can easily access to a charging slot without a jam. Since UAVs in setting 1 prefer to charge, it goes charging frequently, which results in poor service coverage as most of the time UAVs are hardly serving. So, the coverage with ample charging slots in setting 1 is much worse than in setting 2. The result further tells us that, whichever number of charging slots there is, our proposed approach can outperform by adjusting the serving game properly. Finally, we've reached to the conclusion. In order to maximize rechargeable UAV service coverage, we first model the problem into a non-corroborative game. Secondly, we prove the non-corroborative game to be an exact potential game where at least one Nash equilibrium exists. Finally, our proposed approach can manage to reach a Nash equilibrium in a distributed manner. In the future, we will consider a nonlinear energy consumption model which is closer to real-life situations. And this brings us to the end. I'd like to thank you for your time and attention today.